Welcome to the first part of the problem-solving session for chapters 31 and 32. Let's begin with the first question. Here we are given a coil that consists of 200 turns of wire. Each turn is a square that has a side equal to 0.18 meters. Suddenly, a magnetic field that is perpendicular to the plane of the coil, which, by the way, would be parallel to the area normal of the coil, is turned on and changes uniformly from 0 initially to 0.5 Tesla in a time of 0.8 seconds. And we're asked to calculate the magnitude of the induced EMF in this coil while the magnetic field is changing in time. And next, if the ends of a coil are connected to a resistor as the magnetic field is changing, what will be the associated induced current through the resistor? Okay, well, we use Faraday's law in the first part. Here we are. Faraday's law tells us that the EMF that is going to be induced will be equal to the negative of N, the number of turns in the coil. And because we are told that the change occurs uniformly, we can work with the average change in the magnetic flux. So the next thing we want to ask ourselves is, what is it that's changing in the magnetic flux? Well, of course, the change is coming from the change in the area. And that change in area is, not the change in area, the change in the magnetic field through the area of the coil. And that change in the magnetic field can be calculated as delta B over delta T, and that multiplies the constant area of the coil times the cosine of the angle between the area normal and the magnetic field, which, by the way, is 0 degrees because the area normal and the magnetic field are parallel. That occurs when the magnetic field is perpendicular to the surface of the area itself. Well, let's go ahead and substitute in our values. Minus 200 turns times the change in magnetic field. And let's see, we are going from a B final, which is 0.5 Tesla, minus a B initial, which is 0, divided by the time for this change to occur, which is 0.8 seconds, times the area of the coil. Well, the length of each side, and it's a square, is 0.18 meters. So we take 0.18 meters and we square that, times the cosine of 0, which is 1. Multiplying out the terms, we get an EMF of minus 4.5 volts. And notice that the unit volts here, V, is equal to the Tesla times the meter squared per second. So in other words, these two units are entirely equivalent. Because we are writing the induced EMF, we are going to go ahead and express it in terms of volts. Well, in the second part of this problem, we are told that this coil is going to be connected to a resistor, and we're asked to determine the current. Well, we use Ohm's law. The EMF, which is induced in the coil, it doesn't matter how it got there. The fact that there is an EMF through the ends of the coil means that with the resistance of the resistor taken into account, means that we're going to have a current flowing through. So we want only the magnitude of the current, because remember, our current is always presumed to be due to positive charges which are moving. So we're going to just write the magnitude of the EMF here, and we get a current of 2.025 amps. Next question. In question 2, we are told that there is a conducting wire which has been bent so that some part of it forms a closed loop in the presence of a magnetic field. The value of the magnetic field is 0.55 Tesla. And notice that the magnetic field denoted by these little X's right here, this is our external magnetic field, is in the minus K hat direction. Well, it cuts through the circular area of the coil, and because the coil is a conductor, that means we're going to have an EMF as well as an induced current. But only when something in this flux, that is the magnetic field cutting through the area, changes in time. So let's find out what is going to change in time. Well, we're told that the radius of this circle is 0.2 meters, but a student is going to grab each end of the straight part and is going to pull it taut so that the radius will shrink to 0. And it's going to take 1/4 of a second for that change to occur. So in this case here, what we can see is that it is the area which is changing in time. That is, the area that's exposed to this external magnetic field. And if we write down Faraday's law, the EMF equals minus N times the change in the magnetic flux. And again, we're going to treat it as a uniform change in magnetic flux. And the change in the magnetic flux is occurring not because the magnetic field is changing, but rather because the area exposed to the magnetic field is changing in time, times the cosine of the angle between the magnetic field and the area normal, which you can see is 0 degrees, since the magnetic field is parallel to the area normal. So we put in our values. We've got minus. Our N here is just 1 because we only have really one wire making up one loop. The magnetic field is 0.55 Tesla, and it's constant. The area is, let's see, well, pi times the final radius is 0, right? So pi times 0 squared is 0, minus pi times the initial radius, which was 0.2 meters, and we're going to square that, divided by the time for that area to shrink down, which is 0.25 seconds. And this right here gives us the delta A over delta T times 1, because the cosine of 0 is 1. We multiply everything out, and we get this negative multiplied by this negative gives us a positive 0.276 volts. That is the EMF which has been induced while the area was shrinking to 0. Next question. Here we are told that there is a loop of wire that makes up an area where there is a magnetic field that is perpendicular to the plane of the loop, meaning parallel to the area normal of the loop. But the magnetic field varies in time according to B as a function of time. Let's go ahead and write it as a function of time. A constant B max times E, and this time this E is the natural log E, to the minus A times T, where little a is also constant, like B max. And we're told to find the induced EMF in the loop as a function of time. And here the area of the loop is not going to change in time, and neither is the orientation of the loop with respect to the magnetic field. So to get the induced EMF as a function of time, this time we're going to take the derivative because we want the instantaneous values. But the magnetic field as a function of time has been given to us, so this should be a relatively straightforward derivative. So this time we want d phi of b with respect to time. Well, let's see. There's only one loop, so our n is just equal to 1, okay, minus 1. And let's go ahead and just write an expression for the change in the magnetic flux, with respect to time. We're here now dB dt gives us the change in the magnetic field with respect to time, times the area, which doesn't change, times the cosine of the angle between the area normal and the magnetic field, which does not change either. So let's see, we've got minus 1 times the derivative of B max times e to the minus at with respect to t, and times a times 1 here, because the cosine of 0 is 1. So let's see, we've got a minus, well, B max is constant, so that comes out of the derivative. So let's write it here, B max. The derivative of e to the power minus at is going to be minus a times e to the minus at. And that gets multiplied by a, the area of the coil. Well, let's see. Now we can, this negative can multiplies that negative. We get a positive B max times e to the minus at times the area of the coil. So we have the EMF as a function of time. Next question. Here we are given a conducting ring which is coaxial with a solenoid, and the solenoid is connected to a source of EMF so that there's current through the solenoid. But what is going to happen is that the current through the solenoid is going to be changing. So in other words, the source of the EMF that is producing the current in the solenoid is variable. So a variable power box, for example. And this variation in the current is going to produce a changing magnetic flux through this conducting ring. Okay, so let's read the problem and kind of examine our diagram and see what is actually going on before we actually begin to solve these problems. We are told that a conducting ring with a radius of 5 e to the minus 2 meters, that's this thing right here, this is our ring, okay? This is our ring, has a resistance R, which is 3 e to the minus 4 ohms. So the ring has a resistance R, which is given above. It is placed on top of a long solenoid. The solenoid has N turns, the number of turns being 1,000 turns per meter, and it has a radius of 3 e to the minus 2 meters. So this is the radius of the solenoid, radius of solenoid. The radius of the ring is, of course, larger and larger than the radius of the solenoid. We're told to assume that the component of the magnetic field through the solenoid has a value of 1/2 mu naught N times the current through the solenoid, and the half comes from the fact that the solenoid is very long, so by the time the magnetic field cuts through this ring, it already has lost half of its value. So in other words, the magnetic field is strongest at the center of the solenoid and right along the axis of the solenoid. And as we move away from the axis and towards the ends of the solenoid, the magnetic field drops down to 1/2 of its maximum value. All right, so here's what we have happening. We have a current which is changing through the solenoid. Now, if we just consider, for example, from chapter 30, the direction of the magnetic field that's associated with this solenoid here, we see that the magnetic field is downward. So the magnetic field of the solenoid points downward. Okay? Now that means that there is a magnetic flux that cuts through this coil. And here I can also draw the magnetic field of the solenoid so you can see it here at the location of the ring. So it points downward and therefore produces a magnetic flux through the ring. However, because the magnetic field lines of the solenoid are so tight, what is going to happen is that the magnetic flux through the ring is really only going to be confined to a small area of the ring. So in other words, if this is the ring itself with its radius r of ring, because of the magnetic field at the solenoid being so densely packed, only really this area of the ring will be exposed to a magnetic flux. And this, of course, is the area, I'm going to just put a radius here, is the area of the solenoid. So only the radius of the solenoid cutting through the ring is what is going to constitute a magnetic flux. Now, to get an EMF through the ring, we need to have the magnetic flux through the ring changing in time. Well, here's where the problem begins for us. We are told that the current through the solenoid changes in time at a rate of 270 amps per second. And we're asked to determine the changing magnetic flux through the ring as a result of the current through the solenoid changing in time. So in other words, as the current through the solenoid changes, so does the value of its magnetic field, and that magnetic field changing is what changes the magnetic flux through the ring. Okay, so we are told that the current is increasing because they've given us a positive value. The current through the solenoid is increasing at a tremendous rate. In fact, 270 amps in 1 second? Wow. All right. Well, let's see. If that is how the current through the solenoid changes in time, how does the magnetic field of the solenoid change in time? Well, let's see. We know from chapter 30 that the magnetic field through the solenoid is mu naught little n times I, but because I is changing, the changing magnetic field through the solenoid will be the changing current through the solenoid with respect to time. Well, now that we have an expression for how the magnetic field of the solenoid changes in time, let's look at the changing magnetic flux through the ring. So now we focus on the fact that it's the magnetic field that changes, so delta B of the solenoid with respect to T times the area of the ring, but here we have to be very careful because it's not the full area of the ring. In fact, it's the area inside the ring where the solenoid fits in. So I'm going to change that to the area of the solenoid times the cosine of the angle between the area normal of the ring and the magnetic field, and these are parallel. So let's go ahead and substitute mu naught n delta I of the solenoid with respect to time times the area of the ring for which the solenoid cuts through, and that's going to be pi times the radius of the solenoid squared times 1, the cosine of 0. Well, we're ready to substitute our values. Mu naught is 4 pi e to the minus 7. The little n, the n of the solenoid, was given to us as 1,000 turns per meter. The change in the current through the solenoid, 270 amps per second, times pi, times the radius that the solenoid cuts through, which I'm going to put as the radius of the solenoid, 3e to the minus 2 meters. And we square that. And that gives us the value, provided I have put all the numbers in the calculator correctly, 4.80 e to the minus 4 Tesla meter squared per second. That's our changing magnetic flux. Well, the next part says, what is the induced current through the ring? Okay, well, because we have an induced EMF, and what is that induced EMF, by the way? Well, it's going to be the negative N times the change in the magnetic flux with respect to time. Well, we only have one ring, so N is equal to 1 times 4.80 e to the minus 4. And this time, I'm going to write the unit as volts because we're specifically referring to the EMF, and it just sounds better. Well, the induced current, therefore, using Ohm's law, will be equal to the magnitude of the induced EMF divided by the resistance of the ring. Well, the magnitude of the induced EMF is 4.80 e to the minus 4 volts. The resistance of the ring is 3 e to the minus 4 ohms, and that gives us a value of 1.6 amps. The last part of this problem asks us to determine the magnitude of the induced magnetic field at the center of the ring. And so we come over here, the induced magnetic field, because the ring is a circular loop. If you recall from chapter 30, we saw that we can determine the magnetic field at the center of a circular loop, and here let's put I and D for induced, so you don't get the confused with I in, which we have used before in the past when we were referring to direction into the board, or in as in Ampere's law. So this is 2 times the radius of the ring, and this time we're using the radius of the ring because we want the magnetic field at the center of the ring, and that magnetic field is the induced magnetic field. 4 pi e to the minus 7, and that is of course because of the induced current, 1.60 divided by 2 times 5e to the minus 2 meters. Well, let's see, this 2 cancels 2 of those. We multiply our terms and we get 2.01 e to the minus 5 Tesla. Well, this concludes the first part of the problem solving session for chapters 31 and 32. Until next time.